Hey guys, welcome back. Earlier this week we looked at the features of the sun and you drew me a sketch, hopefully anyway, that described a few of the sun's layers and some of the features you'd see. So I'd like to explain those with a little more depth today and try and explain why they happen, not just what they are. And then eventually what we're going to do is tie that into, does that affect life on Earth? So for starters, I want to start with this word right here in the middle, plasma. Okay. Now, I know you all know what a solid is. And I think you know that if I heat up a solid, the molecules start to move faster and it becomes a liquid. Now what happens if I heat up the molecules of a liquid? They move faster and now I get a gas. But what happens if you take a gas, like for example, hydrogen? Hydrogen consists of one proton, that is the nucleus, and one electron orbiting around it. What would happen if I heated him up? I mean, he's already a gas. What more can you do to it, right? So you heat it up and he moves faster. But what if I heat it up some more? It's going to make him move, you guessed it, faster. And if I keep heating it up until it's ridiculously hot like the sun, it's going to move so fast, you know what's going to happen to this electron? It's going to get ripped off. And so a plasma is what happens when you superheat a gas. And what it results in is the atoms get ripped apart to the point where the nucleus and the electron are no longer bound to each other. Now, it doesn't tear these particles apart, but what it means is the nucleus starts flying that direction because it's really hot, it's moving fast, and the electron might be going this direction, zooming around, not attached to each other. So the parts are still inside the sun, but they are all separated, zooming around really, really, really fast. So, what is a plasma? It is a superheated gas located in the sun where the particles have moved so fast that the electrons have been ripped off of the nucleus. So what that means is, in the sun, you end up with lots of nuclei, specifically hydrogen nuclei, which are protons. And those protons fuse, which is what leads us to nuclear fusion. Now, in addition, I need you to realize the sun itself, based on what I just said, does not consist of whole atoms. The sun itself is so hot, it's mostly a plasma. Some parts exist as a gas, but the majority of it, as far as we can tell, is a plasma state, which means the sun itself is mostly protons and electrons separated from each other, zinging around real fast. Now, the cool part is, when you get out here to the outer reaches of this star, right, we'll call it the sun, this is the corona of the sun, the outermost part of its atmosphere, so to speak. It is also made of positively charged nuclei and negatively charged electrons, separated from each other because they've been ripped apart and just zinging around. Now, when we get out to the corona, some of them are moving so fast and you're far enough away from the sun's gravity that not only are they moving fast, they're moving so fast they pull away from the sun's gravity. So this guy just shot into space this direction. But up here, I've got an electron shooting that way and I've got a proton shooting this way and there's another one going this way. And so what that means is we have something called the solar wind. The solar wind is when pieces of the sun itself are moving so fast, they escape the sun's gravity and they shoot off into space in all directions. And this happens 24/7. It's happening right now. These pieces of the sun are shedding themselves out into space. Now, if you were in space, this would be a bad deal because it would affect your body the same way as radiation would, which is not something we want. So if you're an astronaut, if you are on a space station, you need to be in a shielded suit or a shielded location. Otherwise, it's like bathing yourself in tons of radiation, which is not a good thing. So in other words, just recap. Sun's really hot, particles move fast, electrons get ripped off, all these particles are zinging around, some of them move so fast they fly off into space, and we call that the solar wind. Now, what does that have to do with wind? Nothing. There's no air, it's not air moving anywhere, it's just pieces of the sun flying off into space. You may be asking yourself at this point, well, if these are so dangerous, why haven't I heard of them? Well, that's because they don't actually reach the Earth. Because remember, these all have a charge, positive or negative, right? Do you know what Earth has around it? A magnetic field, which has a positive end and a negative end. And so what that does is it creates an electromagnetic field around the Earth that repels most of these particles. The ones that do get in come in at the North Pole and the South Pole because that's where the end of the Earth's, so I can kind of draw it here if you want. Here's Earth, Here's a North Pole and South Pole. We have a positive North Pole and a negative South Pole right now. So you get some electrons come in at the North Pole, some protons come in at the South Pole, but for the most part, this magnetic field pushes things around the Earth. So what happens when they do come in at the poles? Well, when they hit our atmosphere, when they hit the oxygen and nitrogen, it gives those atoms energy, and then they're energetic for a moment, but then when they come back to normal and slow back down, they give off light, which we call the northern lights and the southern lights, or the aurora borealis and the aurora australis. So why does the aurora borealis occur? Because the sun creates a solar wind, again, which is pieces of the sun itself flying off into space. Most of them get repelled by our magnetic field and it goes around us, but a few of them will get pulled in at the North Pole and South Pole because that's where our magnetic field enters and exits the Earth. If they do get pulled in, they collide with oxygen and nitrogen atoms. This leads to a reaction that gives off light, and we call them northern lights and southern lights, or the auroras. So that explains plasma and solar wind, but we also want to try and explain sunspots and solar flares. Now, definition-wise, this is easy. What's a sunspot? It's a dark spot on the sun. Yeah, that's a piece of cake, right? A solar flare, it's an explosion on the surface of the sun, also called the photosphere. Those are easy answers. The more difficult answer is why? Why do these things happen? What leads there to be dark spots on the sun? Why are they sometimes there? Why do they sometimes go away? Why are there sometimes a lot? Why are there sometimes none at all? So we're going to dig a little deeper into that. So to understand this, you have to understand that the sun itself has many, many magnetic fields inside of it. And you got to picture as this thing's spinning, like the Earth does, it spins on an axis. Earth is solid though, so as it spins, the whole thing moves at once. The sun is not. So as it spins, the equator is going at a different speed than, say, the North Pole and the South Pole of the sun. So the magnetic fields that are inside the sun itself start to get twisted and twisted and twisted around each other. And when they do, eventually they start to bend, is the best word I have for it. And what you see is there's areas where the magnetic field starts to bend outward. The place where the magnetic fields get bent out and back in, we call sunspots. So when we see these spots on the sun, we know that the sun's magnetic fields are getting all wound up and bound up and twisted. And when they start to twist, they stick out. So I can see those are places where it's sticking out. This means the sun is really, really active. Why do they appear dark though? Think about it. It's a magnetic field. So it's got we'll just say a positive end and a negative end where it's coming out and going back in. If it's positive right here, what it does is it prevents negative particles from rising. That's about half the particles of the sun. So if half the particles are not rising right here, that's half the amount of heat. If you have half the amount of heat, it's going to give off half the amount of energy. Same thing here. This negative area of the magnetic field prevents the positives from rising right here, which prevents half of the energy from coming out of the sun. As a result, you have two spots that are darker than the rest of the sun because they're giving off less heat. So what causes sunspots? Well, as the sun rotates on its axis, the magnetic fields inside it get all twisted up. As they get twisted up, it prevents hot material from rising, which leads to spots that are cooler. So wait a minute. What happens to the hot stuff that didn't rise? It's stuck downstairs, so to speak? What happens as it starts to build up? Well, as best as we can tell is as it builds up, it starts to build pressure until somewhere nearby it's going to go and explode outward. So try and picture this. What's actually exploding outward? Pieces of the sun that have been held down. The pieces of the sun are protons and electrons that get spewed out into space. So instead of a few pieces of solar wind flying out, you've got a ton of them in one direction, which is generally no big deal unless they tend to be aimed towards Earth. If that happens, we say there's a solar storm coming. And there's so many things I could talk about here, but I'll just give you the short version, okay? Here's the short version. What if we had a satellite parked out in Norbury here, which we do? And what if they use electricity, which they do? Remember, electricity is the movement of electrons. So what happens when you got a bunch of electrons coming from the sun and flowing through that satellite? It fries your circuits. That's what happens. It's too much electricity going through at once. So I don't know if you've ever noticed this, but, whoops, ran into my shelf here. Okay. If you've ever seen an image of a satellite, they're always built like this piece of paper. Wide one direction, but very narrow the other direction. That is so when there's a solar storm coming, we can turn our satellites and our space probes this way so that most of the particles pass right by it. And then when it's over, we can turn them back this way and expose our solar panels and recharge our satellites. So, the other thing that can happen is when you have that much electricity pouring in at the North Pole, it can overload the power grid and the power can go out, which obviously doesn't happen too often here because we're not far enough north. But in Canada, this happens, I don't want to say often, but it's happened several times in recent history where places in Canada lose power because of a massive solar storm, because a solar flare exploded towards the Earth. So that is the cause of plasma and solar wind and sunspots and solar flares. But let's backtrack one last time here. A solar flare is an explosion spewing pieces of the sun out into space. What causes a flare? It's not a sunspot, which is what most kids want to say. The flare itself is caused because of those twisted magnetic fields holding material down, which builds up pressure, which leads to an explosion. So, if you think about it, these two don't cause each other, but they are absolutely connected because the twisted magnetic fields that cause sunspots are also the cause of solar flares. So it's not one leads to the next, it's the twisted magnetic fields lead to both of those. And that explains why those features happen.